Plane waves, being infinite in extent, are obviously kind of an idealization or limiting case, albeit a very, very useful idealization. Another kind of wave we see fairly often is the spherical wave. It's sort of like what you might expect a spherical source to produce. So like a light bulb, or the sun, or light glinting off Vince Quo's bald head, that sort of thing. It's actually pretty hard to derive a spherical wave solution directly without using an approximation of some kind, most commonly the so-called paraxial wave equation. Fortunately, when you're solving differential equations, sometimes it's enough to be able to guess at the form of the solution you want, and then you can proceed by construction. The solution ought to have a propagating term like e to the I kr minus omega t, and the overall amplitude of either E or B ought to go like 1 over r, so that the intensity falls off as 1 over r squared. So let's guess something like that for E. Since it's propagating radially, we'll have it be polarized in some direction orthogonal to r hat, like theta hat. Constructing a solution means taking a trial solution and substituting it into the relevant equations to see what, if anything, about the trial solution needs to be changed. So let's substitute our trial E into Faraday's law to get the form of B. Here's del cross E in spherical coordinates. All the terms besides that one are 0. And that needs to be equal to minus dB dt. So you can take an antiderivative and see that to satisfy Faraday's law, we need a B that's basically E with a k over omega out front, polarized in phi hat, which seems reasonable enough. Next, let's check Gauss's law. We're in free space, so we need del dot E to be 0. Del dot E in spherical has 3 terms. The ones involving r and phi derivatives are 0, and then we also have a theta term. You might hope that this would be 0 since our E doesn't depend on theta, but in curvilinear coordinates things aren't always so simple. That last term looks like, which evaluates to, and we really don't have any good way of making that 0. So we're not going to get this trial solution to work out after all. Apparently spherical waves just can't have this simple of a structure. We could go back and iteratively change things and add things and try to get it all to cancel out and work out just right, and it'd be a bit of a chore, but we could do it. But there's a clever alternative that I'm going to steal from Pollock and Stump. We want to construct an E and B that satisfy the wave equations, while retaining a generally spherical shape. Funny thing is, in the Lorentz gauge, the differential equations for A and V look exactly the same when J and ρ are 0, as they are in vacuum. So let's guess the same spherical form for A that we tried before for E and B. All this has to do is satisfy the wave equation for A, and it does, though showing that is a little grindy and I'm going to skip the details. Oddly enough, those grindy details are easier if you let A be in the k-hat direction instead of one of the spherical directions. Given that A, we just have to take the curl of it to get B, and then we can use the Ampere-Maxwell law to back out E. And that leaves us with okay, let me point out a couple of things in this big old beast. So there's a couple of capital C's, which are just arbitrary constants, and then right next to that in the E, there's the lowercase c, which is the speed of light. You'll notice there's mixed real and imaginary terms, terms with and without the I. What's going to happen there is when you multiply across the complex exponential and take the real part, you're basically going to get a mix of sine omega t and cos omega t terms. It's a pretty big, scary equation, but in a little bit of a Christmas miracle, since the A that generated this satisfied a wave-like equation, these end up also satisfying the wave equation. But this right here is the fundamental form of a spherical wave, the E and B fields for a spherical wave. You'll notice that the E field drops off as you go farther away, in contrast to what a plane wave does. Here's a little visualization of a spherical wave. So there's going to be some kind of source, in the dead center, radiating outward in all directions. But again, it doesn't have perfect spherical symmetry because the fields are going to be polarized. The E field, for example, might be polarized in the theta hat direction while the B field is polarized in the phi hat direction. But even so, this is a very spherical kind of wave, and if you imagine zooming way in on it, it's eventually going to be locally flat, and in that limit it becomes more or less a plane wave. So waves, for example, from the sun, which is 93 million miles away, start out being spherical, but by the time they get here, they're pretty damn near exact plane waves. Speaking of limits, why don't we tidy these things up a little bit? Why don't we look at the large R limit, since usually radiative fields are fields that have gone off and traveled some distance away from the source. We call the large R region the radiation zone. So in that limit, the 1 over R terms dominate over 1 over R squared and 1 over R cubed terms. So there's really only a couple of bits and pieces that make it. And those pieces are these. So these have sort of a 1 over R behavior and amplitude, which, if you stop and think about it, kind of makes sense. If you have something like a light bulb or the sun or Vince's head that's radiating in all directions with constant power, the radiation intensity, which is power per area, should decrease as 1 over R squared. And sure enough, the intensity of an electromagnetic wave comes from the magnitude of the pointing vector, which is going to be proportional to E cross B. And so if you have one term, E, that's going like 1 over R, and the B is also going like 1 over R, the intensity goes like 1 over R squared, and life is good. Now there is another limit. When you're in close to the source, the radiative fields actually are not dominant. In there, the 1 over R squared and 1 over R cubed terms are dominant. And the way I like to think about this is that when you're very close to a source, the fields that that source would be making in a static or quasi-static situation will tend to dominate the radiative fields. So if you're in close to an electric monopole, on top of the radiation, you'd see, like a KQ over R field. If you're in close to a dipole, you'd see a dipole field in addition to the radiative field. And if we take our old expressions and take that very small r limit, this is the so-called near zone, we get something like this, which, if you have an exceptional memory, you'll recognize as being actually the electric field of a dipole modulated by some kind of time-dependent term. So in close to whatever source we have, these E fields look like the static fields made by an electric dipole. And what we will eventually be able to derive from first principles is that these solutions do in fact come from allowing a dipole to oscillate and therefore radiate. And so when I write down something like that, where the symmetry is broken by, say, a k-hat vector, that k-hat vector is the direction along which our dipole is oscillating. But that is a story for another day.